Thomas White.
And we are going to be talking about experiment 1, the absorbance spectrum of cobalt-2 chloride. In the beginning of our pre-experiment, by the time you're done with the experiment, you should be able to do the purpose of the experiment, you should be able to know the results and how to discuss them and analyze them, and apply them to the 2 unknown solutions that are within the experiment. Then be able to identify the references that you used. The purpose of the experiment is to define random max of cobalt-2 chloride and determine the concentrations of the unknown solutions that are within. The spectrophotometer is an interaction with matter with radiation and is used to determine the light presence and the amount of absorbance it can determine the amount of particular substance present. So if the light shines through, then you have a better solution. Beer's law is A equals epsilon, concentration and path length, and then absorbance and transmittant percentage have an inverse relationship.
In the experimental, your first step will be a cuvette with water is named blank. Then it is used to zero the spectrophotometer. The second cuvette is then filled with 0.150 molar cobalt-2 chloride. The spectrophotometer is then set to 400 nanometers, and then the cobalt-2 chloride is placed into the spectrophotometer. The percent absorbance, percent transmittance, and absorbance is then recorded from the spectrophotometer, and then it is zeroed and retested with a blank to set it back to 0, and then used with cobalt-2 chloride, and at increasing of 25 nanometers until you hit 600 nanometers. The second part of the experiment is you use graduated pipettes, and they're used to create 8 varying molarities of your cobalt-2 chloride. Each molarity is tested at your lambda max, and then you recorded also percent transmittance and absorbance.
Alright, table 1 shows the correlation between transmittance and percent transmittance and absorbance. As the percent transmittance increases, the absorbance decreases. The results, we did an example calculation, and this was with 400 nanometers present, and it's A equals log of percent transmittance, and the transmittance there was 82, and so the answer was 0.0862. The figure 1 shows the relationship again in a different way, and the wavelength versus absorbance, and it's just spread out more. Table 2 is a construction of the standard curve graph, and it shows the molarity, concentration with molarity is also directly and indirectly related to percent transmittance and absorbance. And as the concentration increases, the absorbance at lambda max also increases, but as the concentration increases, the percent transmittance decreases. And then example molarity calculation was done in test tube 3. And it uses the molarity concentration of MC VC equals MD VD. And we use the calculation to do algebraically, and we end up with the molarity concentration of 0.0600 molarity. And then we did the example test 2 again, and we did it with the A equals epsilon concentration of path length. And we used the values that we got from the chart and everything, and we got 5.28 liters over moles times centimeters. And then this figure 2 graph shows the relationship between absorbance and concentration, and they both have they have a linear relationship. So as one increases, the other one increases too. And then these are our unknown solutions.
These are results with the lambda max of 500 nanometers. Unknown number 45 had a percent transmittance at 22.8, along with an absorbance of 0.640, while unknown number 45 had a percent transmittance of 31.6 and an absorbance of 0.500. These are just showing the 2 unknown cobalt chlorides, 2 solutions used in the spectrophotometer to help us determine the molarity of the 2 unknowns. Using a calculation of our unknown concentrations. Unknown number 45, we have the y equals mx plus b, which is from the linear graph, and then then we substitute basically in the m, the x, and the b with your original Beer's law, because that is technically showing you what the equation is on the graph. Once you plug in your data, you basically plug in showing at the end, concentration equals 0.106 moles over liters, or 0.106 molarity.
And you do the same thing with the unknown 48, which was my solution. And you do the y equals mx plus b, and you put it in Beer's law again, and then you plug in chug, and you get 0.136 moles per liters.
And our discussion questions, number 1, percent transmittance and absorbance had an indirect relationship. For example, table 1 shows the percent transmittance and the absorbance and the relation to them. At the very top, you have 82% transmittance with an absorbance of 0.0840, while as you increase your percent transmittance, your absorbance, or as percent transmittance decreases, your absorbance increases, showing an indirect relationship. Same thing with table number 3. Shows that percent transmittance, the higher percent transmittance had a lower amount of absorbance at the max.
Data gathered from a section of Atlanta max at 500 nanometers. Also, the absorbance was the greatest and the transmittance was the lowest, so it has an inverse relationship. And table 1 showed that. And the same thing basically, as Tommy said, the absorbance was decreased and the transmittance was the highest at 400 nanometers. And then it was the lowest at 500 nanometers, and 17.6 was the percent transmittance, and it was 0.754 absorbance.
As absorbance increased, the concentration also increased. We can see in table 2, concentration as concentration increased, absorbance also increased at Atlanta max. And you can say it in the same way that as your concentration increased, the percent transmittance also decreased. Beer's law is absorbance is strictly proportional to epsilon, and path length and C concentration.
And the concentrations of our known solutions was 1.06 moles per liters and 0.136 moles per liters for the 48.
And the way that we came to those conclusions is through our calculations. This is the results for number 45. Shows us how we got the numbers and everything of that sort. Same way with number 48. Same way. Same procedure, just different numbers.
In conclusion, basically the concentration and absorbance and percent transmittance are directly or inversely related, and concentration and absorbance are related in linear relationship, and concentration and absorbance are inversely related. And then these are our resources for the experiment. We had to recite our chemistry lab book and our lab email. Thank you.